وعليكم السلام ورحمة الله.
Allah يحييكم. So I've started recording. I forgot. I just remembered قبل شوية that I forgot to tell you about the details about the quiz or what is the material. Inshallah, I'll let you know in a few minutes. Okay. I've selected the material and I was planning to send you a WhatsApp message yesterday. I don't know. I got busy with something and forgot to do it. Inshallah, later today. I'll tell you. Okay. So what we were talking about, gentlemen, last class, what we started talking about is the Fourier series. In the last, I think, half hour of the class or so, we started talking about the what we call the Fourier series expansion, Fourier series expansion, to be accurate. And we said that any periodic signal can be expressed as the sum of sines and cosines. And last class, I even ran MATLAB and showed you a tool that I prepared maybe 15 years ago or so that allows you to basically show that any signal can be expressed as sum of sines and cosines. And I promise you, inshallah, I'll go and show you more, let's say, examples on that tool. And during the weekend, I was working on that, that program that I wrote, the MATLAB program. And by the way, you do not need to know anything about MATLAB. And I'm not gonna, if you're interested, I can give you that. But I'm not going to ask you any questions about MATLAB. We're not going to be using MATLAB in the course. Okay, MATLAB is a good tool, but you don't need to know MATLAB to complete this course. So during the weekend, I was thinking, should I focus maybe a little bit on MATLAB, or just ignore it and go to the let's say to the Fourier series topic and explain it? And then I thought that I'll do the following. I'll explain to you the basic concept of the Fourier series, and then I will show you some examples in MATLAB that hopefully will get you to understand the concept better. Yeah? I think the good thing about that program that I wrote several years ago is that it allows you to put any function that you're interested in and immediately show you basically what are the components that you need to add, or what are the sines and cosines that you need to add together with different frequencies, so that you can express that complicated function in terms of sines and cosines. So I'll show you, inshallah, several examples, and hopefully, if you understand those examples, they'll add much to your understanding of Fourier series. Okay. So what I will do at the beginning, gentlemen, is I'll explain to you the basic concepts of the Fourier series, and because just showing you examples on MATLAB is not going to add much unless we talk about what is the Fourier series. Okay. And I was thinking also about how can I explain to you the best, or what is the best way of explaining to you the Fourier series? Why can you express a signal, a periodic signal, in terms of sines and cosines? So this is basically what I'm going to do now. To be able to express to you or to explain to you the concept, let me ask you the following question. Assume that I have a point that is in the XY plane. Yeah? So we have the XY plane. This is the X and Y. Yeah? And I told you that I have a point. Now, we know that there are several ways of explaining or of determining what is the location of that point. This is the point P. One way of determining or telling someone where is the location of that point is using what? What can you do to tell someone about the location of a point in the XY plane, gentlemen? Any ideas?
The
coordinates.
The coordinates, exactly. Okay, the coordinates. So I can tell you. Thank you so much for both of you. Okay, I can tell you what is the value of x. Let's say x. For example, let me just give you an example. Okay, let's say in 3 and 4. So perfect. So by telling you what is the location of that point, or what do the 3 and 4 there represent? Think of the following. This, I'm not sure if you have studied this or not, but think of a vector, a line that goes from the origin all the way to that point. What does the 3 represent, and what does the 4 represent? Anybody knows? I think that you have studied this sometime in the past. With respect to that line, to that vector, let's say. Anybody knows what the 3 represent? Well, okay, if you don't know, that's okay. The 3 represents the projection of that line over this axis. What do I mean by the projection? If you have your hand, for example, okay, assume that you are standing outside, okay, and this is you, let's say. Okay? And you have your hand, let's say, extended like that, right? And the sun is somewhere there. Now the sun is causing a shadow to your hand. What do we call this shadow? Think of the shadow there as the projection of your hand on the ground. Meaning that if I come to this XY plane, if, for example, this vector or this line, for example, if I move the point P up, the projection that that line is making with respect to the x-axis does not change. This projection, this amount of 3 there, basically represents how much does that line in there, which represents the vector from the origin until the point P, how much does it extend in the direction of x? Now, it's not enough if I have a point that is in the xy plane. It's not enough to tell you the projection of that line or of that vector of that point in the x-axis to know what that point or where that point is. You also need the projection of that line on another axis, on the y-axis. Knowing also the projection of that line or of that vector on the y-axis now allows you to determine any point in a plane. In any plane that can be described by x direction and y direction, you only need 2 positions to determine any point in that plane, right? In any sheet of paper, if I give you a sheet of paper and tell you what is the location of a point there, all you need is 2 locations, or what we call 2 coordinates, the x coordinate and the y coordinate. You do not need a z coordinate. Why? Because this sheet is just 2 dimensions. But if I wanted, for example, to explain to you the location of a point in space in the x, y, and z, let's say coordinates, then now I need 3 coordinates. Why? Because one of them will express how much do I need to move from the origin in the x direction. The other one will tell me how much I need to move in the, let's say, from the origin in the y direction until I hit that point. And the last one is how much do I need to move from the origin in the z direction to hit that point. And basically the projection of all of those or let's say those 3 projections, if you combine them all together, you'll get a point that represents the location of, or you'll get basically the point that you need to describe. So what are those? Those are nothing but what we call the projections of a vector that I'm sketching in here in red in 3 dimensions along the x direction, the y direction, and the z direction. Now, what do we notice about the x, let's say x axis, y axis, and z axis? They are all perpendicular to each other. In fact, whenever you want to express the location of any point, you'll understand, by the way, why am I talking about coordinates when we're talking about signals. Just give me a few minutes. Okay? So whenever you want to describe any point, gentlemen, in xy plane, for example, you need to have 2 coordinates. And the x, y, and y axis have to be perpendicular to each other. Always. Okay? Now, what happens if you do not use perpendicular axes? For example, assume that I told you I have the following axis. This is the x-axis, and this is the y-axis. This is, by the way, this is in the same screen plane. And this is not, I'm not talking about an x, y, z like that. Okay? Let's say the x and y there are separated by 45 degrees in here. This is what I mean. Okay? Now, what happens if I have a point there and I want to express it in the x and y coordinates, let's say? Can I do it? Yes, certainly I can do it. This, in fact, if you think about it, sorry, my apologies for that. Okay, so if I have any point P, the P there has also an let's say an x projection, which is basically represented by the blue line in here, okay? And it also has a y projection, which is represented by the yellow line there. Yellow is not clear. And it has a y projection that is expressed by the green line there. Okay? Now, what's the problem with using coordinates that are not perpendicular? Let's see what happens in here, for example. If I come to the xy plane, I have the point P there. Okay? This is the point P. And I decided to move P along, or let's say parallel to this axis. Okay? yeah, basically I move it in a way that keeps it at the same distance from the y-axis. What happens to the x-coordinate or the x projection? It remains the same, right? So moving a point up and down changes the projection in the y direction, but it does not change the projection in the x direction. And moving the point horizontally this way changes this projection, but it has no effect on the y projection. This is the idea of using perpendicular, let's say, axis. The x-axis and the y-axis are perpendicular to each other. And if I go to 3 dimensions, like in this situation, it's the same. If I move this point in like that, parallel to the x, then only the x coordinate or the x projection, this projection here, will change. But the y projection and the z projection do not change. Again, if I move it parallel to the y-axis and move it upwards, only the y coordinate will change, but the x and z coordinates do not change. And the same thing happens with z. But what happens if I have a situation like this? If I move let's say the point P parallel to the x-axis, clearly this line here or this projection will change. It will increase or decrease depending on whether you move to the right or move to the left. But will the projection, will the green line there increase in length or remain constant? Will it change in length or remain constant? Clearly, if you move this point in there, the projection on the x direction will change, and also the projection in the y direction, let's say, will change. That's why using non-perpendicular coordinates, coordinate system in which the x direction and the y direction are not perpendicular to each other, is always not preferred, because you can always, or changing one of the coordinates, changing, let's say, the projection in one direction will also affect the projection in other directions. Okay? So far I have explained to you what happens with vectors. The same concept can be extended to signals. Now you may say, how do signals, we're talking in here about an x coordinate and a y coordinate, okay? And we're projecting a point in the x direction and y direction. Can we project a signal along the directions of other signals? And the answer is yes. Okay? And this is why I talked about x and y coordinates, because the same concept can be extended to signals. Do you have any questions so far, gentlemen, on what I've mentioned? Before I go to the, what do we mean by projection of signals in the along, let's say, the direction of other signals? Do you have any questions? Okay. Now, think of two signals, or we can define the following concept, that two signals can be orthogonal to each other or perpendicular to each other. We understand what the meaning of two lines are perpendicular to each other. This means that the angle between them is 90 degrees. Whenever you have two lines in which the angle that separates them is 90 degrees, then those two lines are perpendicular to each other. How can two signals be perpendicular? The concept may not be straightforward, and you may not understand it very clearly, but don't worry. Even if you don't understand it, I just want you to understand where does the Fourier series concept come from. What's the concept of two signals being orthogonal or perpendicular to each other? In the case of vectors, if I have two lines that are perpendicular to each other, what is the projection of a vector that is on one of those lines? What is the projection of that vector along the direction of the other vector, if they are perpendicular to each other? How much is the projection of this point P along the direction of, say, this is the xy plane, and I'm interested in a point P that is on the y-axis. What is its projection along the x direction? Clearly it's 0, isn't it? Yeah. It is 0, isn't it? Okay. This line, the vertical line there, if you look, assume that the sun is exactly above the y-axis. How long is the shadow of this line? Now, if the line is like that, the shadow, if the sun is exactly along the y-axis, or let's say above the y-axis, the shadow is going to be something like that. Okay. So think of this as the projection. This is why I talked about you standing in the sun with a hand that is extended. Yeah? What I meant by that is that the shadow, think of the shadow as the projection of this along this direction. And if you have a sun that is somewhere here, yeah, the shadow of this line along the y-axis will be the projection along that direction. Now, if you have a line that is exactly on the y-axis, and a point P that is somewhere there, clearly, if the sun is on top, the projection of this vector is going to have 0 length. And basically, the projection is 0. The x coordinate, or let's say the x projection of that vector is going to be equal to 0 because that thing is perpendicular. Okay? So the concept of two lines that are perpendicular to each other, when you project one of them along the other, you get 0. Let's try to extend this on signals. And let's talk about periodic signals. What are, well, the concept can be extended to any signals, even if they're not periodic, okay? But since we are talking about the Fourier series, and Fourier series are periodic signals, and the Fourier series expansion expands a signal that is periodic using periodic functions. So let's talk about periodic signals. Assume that I have two functions. And let's say, for example, that this is the first function. Select blue. Okay, let's say that this is a periodic signal, so it repeats, but I'm only interested in a specific period of it. Let me call it T0. And let's say I have another signal in the same region, okay, between 0 and T0. Those two signals are called orthogonal or perpendicular to each other if the following happens. Let's say that this is x1 of t, and this is x2 of t. If you do the following, if you take x1 of t and multiply it by x2 of t and integrate from 0 to t0 over a specific distance, let's say, a distance that is equal to t0 or a duration that is equal to t0, with respect to dt, if this integration becomes equal to 0, we say that the green signal and the blue signal are orthogonal to each other. This is not that different from the concept of vectors. Vectors, if you project one of them along the direction of the other one and you get 0, we say that they are perpendicular to each other or orthogonal to each other. Orthogonal and perpendicular mean exactly the same. Okay, I'll come to your question, Muhammad. Okay, so for signals, it's exactly the same, but signals are functions of time. So whenever you define two signals that are orthogonal, or whenever you define two signals and you want to determine whether they are orthogonal or not, multiply the two signals together and integrate them over a specific period, t0, let's say. We'll define what t0 is, yeah? But integrate them over a specific t0, integrate the product over a period t0. If the integration becomes equal to 0, this means that the two signals are orthogonal. If the integration is not equal to 0, this means that they are not orthogonal over that period. Maybe they are orthogonal over some other period. Meaning, for example, if I integrate two signals from 0 to 1, and I get 0, I'll say that they are orthogonal between 0 and 1. If I integrate them between 0 and 2.3, for example, and get 1.3, this means that between 0 and 2.3, they're not orthogonal. But it doesn't mean that two signals that are not orthogonal over a specific period will never be orthogonal. You could, and I'll show you, in fact, this example, I'll apply it to the sine and cosine in a minute. You see that two signals that are, when you multiply them or together and integrate them between 0 and a specific period, a specific amount over a specific duration, if the result is equal to 0, we call those two signals orthogonal to each other. Okay, تفضل محمد.
دكتور يعني if I have two signals and one is orthogonal to the other, so could it be delayed with the same version of that signal?
Yes, yes. Okay, thank you for pointing this out. Yes, orthogonality, gentlemen, can be multiple. Let's say, if I give you a signal and tell you, well, go and discover for me a signal that is orthogonal to it. One way is finding a completely different signal, a signal that is completely different in shape. You could do this. Sometimes some signals, if you just delay them by a specific amount, the result becomes orthogonal, as you'll see, inshallah. Thank you so much, Muhammad, for pointing this out. In fact, this is going to be one of the things that we'll investigate. Okay, so you could have signals that are orthogonal just by delaying them. They become orthogonal with copies of them, let's say with delayed copies of them. Okay. Let me show you some orthogonal signals, and once you understand this, you'll inshallah be able to you'll understand the concept of the Fourier series. And I'll try to be as accurate as possible, because for orthogonality, it's very important that you you become accurate. If I sketch a signal 1, let's say x1 of t is equal to constant 1, and x2 of t is equal to cosine pi t, or let's say 2 pi t. Yeah, clearly, the first signal is just a constant. So the period is not really defined for a signal that is a constant. Okay, I mean a DC value does not really have a period, but you can think of the period to be any quantity if you want. You can think of this signal as repeating every second, or repeating every 2 seconds, or repeating every half a second. Okay, but the period actually is not defined for DC values, let's say. Okay, so forget about the first signal. But the second signal is periodic, and I'll sketch, by the way, both to show you. Okay? The second signal is periodic, so we can define its period. And we know that the period t is equal to 2 pi divided by the frequency, which is equal to 2 pi. And I selected it to be this so that it becomes equal to, yeah, it becomes simple. So the period for the second signal is equal to 1. I'll show you that those two signals are orthogonal over a duration of 1 second. Let's sketch both. And I'm only interested over the period between 0 and 1 second. So I'll only sketch them over that duration. Now, if you sketch over the duration of 0 to 1 second, the first, let's say the first one is a DC, so it's a constant 1. And the second one is just a cosine, so it looks like this. Right? Yeah. Where this is 1 and this is -1. Let me just delete the thing, this stuff that is there. Where this is 1 and this is -1. Now this is the plot of the two. Now if you multiply them together, what will you get? Whenever you multiply any signal by 1, you get the same signal. So the product of those two, if I multiply them, I'll get the following. And let me do it maybe in black. So this is the product of the two. And this is 1, this is 0.25, this is 0.5, this is 0.75, and so on. Okay? This is 1 in here, +1, and this is -1. Okay? Now, if I integrate the product, this is the product of the two. This is not, well, it happens that the product is equal to the second signal, because the first signal is equal to 1. But if I multiply them, I get the second signal, basically. And if I integrate the signal, what will you notice? I'll get an area here. I'm not going to do the integration, but you know that if you integrate a cosine over one complete period, you should always get a 0, right? And this is very clear because if you integrate, this area in here will be equal to this area. One of them is above 0 and the other one is below 0. And this area in here will be equal. So, sorry, maybe the plot is not perfectly correct. Okay, but you can see that those two, let's say the blue region or the black region there will cancel, and the orange region will cancel because I have positive and negative and positive and negative, right? So the integration of both of those, if I integrate it from here to here, I get 0. So we say that those two signals are orthogonal over the period from 0 to 1. In fact, they are orthogonal over any duration as long as that duration is equal to 1 unit. Meaning that even if I integrate it not from 0 to 1, but if I integrate it from 0.1 to 1.1, do you think that they will be orthogonal or not? What do you think?
Yes.
Yes.
Yes. Why? Because this repeats, right? In here it repeats. So if I start at 0.1, this means that I'm starting somewhere in here. But I'm ending طبعا 1 unit later. I'm not ending at 1, I'm ending at 1.1. Okay? So whatever thing that I missed in here has been obtained from here. So in fact, those two signals are orthogonal no matter what interval you select, as long as you select an interval that has a duration of 1. Right? Then what if I take an interval that is equal to 2? Are they orthogonal? 2 units.
Yes.
Yes, again, they are orthogonal. Because once two signals are orthogonal over a duration of 1 second, for example, then and they're periodic, this means that if you take the next second, exactly what happened in the first second will happen in the second second. So again, the integration will become equal to 0. So in fact, those signals are orthogonal over a duration of 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and so on, and any integer number of seconds. However, are they orthogonal over the duration from 0 all the way to 1.3, for example? Do you think that they will be orthogonal? Or let's take it 0.9, for example, 0.9. Do you think that they will be orthogonal in this situation?
No.
No.
No, they are not. Why? Because you see, you haven't completed that second, let's say, you haven't completed the period. So in fact, you're stopping somewhere in here. This is the 0.9, let's say, right? So you'll get some area here, but the point is that this area will not cancel this area. Those two areas, this one and this one, cancel. But this one and this one, sorry, okay. The yellow region in here does not cancel the yellow region in there. The orange in here cancels this orange. Yes, that's true. But there are two regions there that do not cancel. So if you do the integration, you're not going to end up with 0. You're going to get either positive value or negative value, depending on how much did you take, or where did you start and where did you end. By the way, in this situation, it's going to be a negative value because the negative region here has more area than the positive region. This is smaller than this one. But if I started, for example, at a different point, maybe if I started a little bit to the left or a little bit to the right, you'll possibly find that the integration will end up with a positive value, not necessarily negative. Okay? But the important point here is you will not get a value that is equal to 0. No matter what you do, you'll not get a value that is equal to 0. So clearly, those two signals are not orthogonal over a duration of 0.9, but they are orthogonal over a duration of 1, which means that they are orthogonal over a duration of 2 and 3 and 4 and so on. Okay. In fact, now I have shown you that those are orthogonal over a duration of 1. Are those the only two signals that are orthogonal? No. I could have taken this and replaced it with a sine. 2 pi t. Trust me, they will also be orthogonal. Now, in here, it requires a little bit more, let's say, work to show. I'm trying to erase, but my computer is not. Okay. This is the cosine, so let me erase everything that I don't need. And let me sketch the sine. Let me sketch it in green. I'll try also to be accurate. The sine is nothing but a shifted version of the cosine, right? So like this. Now, it's not obvious here that they are orthogonal. But if you multiply them, I'll just show you. Maybe I'll multiply them by several points of them, just to prove it to you. Okay. If I multiply several points, I'll get the product in here equal to 0 because I have 0 in here multiplied by 1, so 0. In fact, the peak value here will happen at this point. In here, if I take this, it will be somewhere in there. Whatever it is, it's going to be, I think, 1 over square root of 2 multiplied. I think something like 1/2. If I'm not mistaken, I think 1/2. Because 1 over square root of 2, this is going to be angle 45. And this is going to be angle 45. Is it angle 45? Yes. In which the sine and the cosine are equal to 1 over square root of 2. Right? So 1 over square root of 2 multiplied by 1 over square root of 2, you get 1 over 2. Now at this point, I'll get 0 again. So at this point, I'll get 0 here. This point, I'll get exactly the same as 1/2, but negative. In here, and there, I'll get minus 1/2, I think. Minus 1 over 2. In here, I'll get 0 again. Yeah. In here, I'll get this. Both of them are negative at this point in here. I don't know if you can see it. Both of them at this point in here are negative. Minus 1/2, minus 1 over square root of 2 multiplied by minus 1 over square root of 2, you'll end up with positive. Positive 1/2. Yeah? And in here, I'll get 0. And in there, I'll get minus 1/2. And finally, at this point, I'll get 0. Now, if you connect those, or if you find it more accurately, this is how it will look like. Something like this. I think. I hope I haven't made a mistake, but something like this. Yeah. And clearly now, if I integrate, this region here will cancel this, and this will cancel this. In fact, this is going to be a sinusoid, by the way, with double the frequency. Sine multiplied by cosine, you can always use trigonometric identity. 1/2, I don't know, cosine the sum plus 1/2 cosine the difference, or something like this, okay? So you'll end up with a sinusoid that has double the frequency. Okay? And if you integrate that sinusoid with double the frequency over one complete period of the original sine or cosine, you'll end up with integrating two periods of the double the frequency sine. But the important thing is that you'll end up with 0. In fact, those sine and cosine are even orthogonal over smaller periods, over 1/2. If I only take this period from here to here, the two are orthogonal. So if they are orthogonal over this period, they are certainly orthogonal over this longer period. Double that period. Okay? So you see, the sine and cosine are also orthogonal. Now I'm going to give you something that you need to understand in here. In fact, sine 2 pi in t is orthogonal with sine 2 pi kt for any value of n and any integer value of n and any integer value of k that are not equal to each other. Meaning, plug in, for example, sine. If someone asks you sine 2 pi 5t and cosine 2 pi 7t, are they orthogonal? Yes. Trust me on this. Multiply them and integrate them over 1 second, you get 0. Okay? Sine, change the 5 in here to 9 and change this to 3. Are they orthogonal? Yes. And so on. Put any value in here and any value in there, they are always orthogonal. The only, in fact, for the sine and cosine, even if they are equal, even, for example, if you put 3 and 3, they are equal. What came to my mind is I was thinking that I was talking about cosine and cosine. Clearly, cosine. Okay, the other thing that I did not mention so far, in fact, I'll tell you this. Cosine and cosine are also orthogonal, but now you have to make sure that those are not equal to each other. If they are equal to each other, you get cosine squared. And when you multiply cosine by the same frequency and same phase, okay, you end up with something that is always positive, right? Cosine squared is always positive. And cosine squared, when you integrate it from 0 to 1, in fact, if you integrate it over any interval, it's not going to give you 0. That's why a signal is never orthogonal with itself. A signal is never orthogonal with itself. But a sine, let's say a cosine, with another cosine that have different frequencies, like for example 3 and 5, are orthogonal. 7 and 9 are orthogonal, and so on. Now, what is the concept here? Why are we talking about orthogonality of those signals? Since those signals are orthogonal, any other signal now, think of it this way. Because we have defined, I don't know if I erased it, yeah? Because we have defined the x-axis and the y-axis are perpendicular to each other, we were able to represent any vector in terms of an x projection and a y projection. Think about it this way. Because we have defined an x-axis and a y-axis that are at 90 degrees from each other, any point now, I can always say that this point can be represented as an x-coordinate and a y-coordinate. Take another point, this also has a different x-coordinate and a different y-coordinate, and so on. And by knowing those coordinates, the x and the y for any point, I will be able to determine where that point is. Or basically, I will be able to sketch that point, let's say, in the xy plane. The same concept applies when it comes to those signals. Where's the sketch? Okay. The same thing applies in here. Since those signals are orthogonal to each other, the sine, let me say it this way. The one cosine 2 pi omega t, omega 0t, let's say. Okay? Those are orthogonal over a period t0, which is equal to 2 pi over omega 0. If you trust me on this, if you multiply those and integrate over one complete period, where the period t0 is equal to 2 pi over the frequency, you get 0. Not only those two signals, also cosine 2 pi 2 omega 0t. Double the frequency. If I take a cosine and cosine of double that frequency and integrate over the same period t0, they will also be orthogonal to each other. Not only that, take also cosine 2 pi 4 omega, not 4, even 3 omega 0 t. And so on. Any of those signals until infinite, until I can put any number in here, until infinity. All of those signals will be orthogonal with each other. meaning this is orthogonal with this, orthogonal with this, orthogonal with this. Sorry, someone called me and I opened the phone by opened the line by mistake. Okay, so the one is orthogonal with this, orthogonal with this, orthogonal with this. This one is orthogonal with this, with this, with this. In fact, any two you pick from this list, they'll always be orthogonal. Okay, not only those, but even if I take now the sines also. Okay? If I take the following sine 2 pi omega 0 t and sine 2 pi 2 omega 0 t and sine 2 pi 3 omega 0 t and so on until infinity. All of those, and now I have infinite number of signals in there. Pick any two of them, they'll always be orthogonal with each other as long as you integrate over one complete plane. Think now of those orthogonal signals as x direction, y direction, z direction, w direction, m direction, and so on. As if you have an infinite dimension plane, an infinite dimension, let's say, coordinate system. In the case of a paper, we only have x and y. In the case of space, we have x, y, and z. In the case of those signals, each one of those, think of this as a specific dimension, let's say. Okay? Think of this one as another dimension, perpendicular to it. Think of the third one here as a third dimension, perpendicular to both of them. Those. Think of the fourth one as another perpendicular direction to all of the previous ones, and so on. And the same thing with the sines. So now, any periodic signal, you can always represent it in terms of combinations of all of those. Okay? This is basically the concept of the Fourier series. It basically says that any signal now, you can always represent it, any periodic signal, you can always represent it as sum of infinite, possibly infinite number of those. Not only one or two. If you only use one or two, it's an approximation. It's like, for example, if I tell you the following. In the xy plane, xyz plane, I'm sorry, xyz, let's say, coordinate system. If I have a point which is somewhere in here, hopefully I can sketch it properly. In 3 dimensions, assume I have this point. Okay? This point, which is represented by this vector in here. Okay? And someone told you, well, I want you to represent the green vector there, but only using x coordinate and y coordinate. You can tell them I cannot. If I do, if I find the x projection, which is this green line, or let me put yellow in here, the yellow, and the y direction, which is the red in here, not yet red, I mean orange, those two become only an approximation for this green curve or green vector, because they're not able to represent it completely. But at least in the xy plane, yes, they will be able to represent that vector. But clearly, they don't represent the vector itself. Think of them as an approximation for it. To be able to represent this green arrow or green vector, I need 3 coordinates. Now, if you have 5 coordinates, or let's say 5, what I mean by you have 3 dimensions. If you are living in a 5 dimension, let's say, space, and someone asks you to represent something only using 3 dimensions, you're going to tell him that whatever I represent is only going to be an approximation of that. You need 5 dimensions to represent it. The same concept applies in here. Okay? In here, I have infinite dimensions. To be able to represent a signal perfectly, any periodic signal using those, I need theoretically to represent it in terms of all of this infinite sum. If I use less than infinity, my representation is just going to be an approximation. It's not going to be perfect. It's going to be close to. The more dimensions you use, the better your approximation are. Okay, Akhwan? Do you have any questions so far? Any questions, gentlemen? Further, Abdurrahman.
Yes. What's the relationship between this and the t naught equals 2 pi over omega naught?
Okay. Thank you so much for pointing this. Okay. What I was saying, gentlemen, is that those are orthogonal over this period. We saw, for example, for this, this example and this example, I said that the 1 and the cosine 2 pi t were orthogonal over 1 second, right? But when I took the duration of integration to be equal to 0.9, they were not orthogonal, right? Agree with me, Abdurrahman?
Right, yes.
Okay. The same thing here. What I'm saying is that those are orthogonal as long as you integrate over a period of t0, which is, let's say, from 0 to t0, or from 1 second to 1 second plus t0. And the duration of the integration that you have to take has always to be, let's say, t0 or multiple of it. Not 0.9 t0, not 1.1 t0.
Yeah, I see.
Okay. Okay. So now I think we are ready to go to that, let's say, MATLAB code, because now I'll be able to explain to you what is going on in that code. Maybe it was a mistake when I showed it to you last time, because I just started talking about the Fourier series and I just showed you graphs and so on. You didn't understand the concept. Let me show you now. Let me run MATLAB. I ran MATLAB, in fact, before we started, because I know that it takes a while. Yeah. And let me share with you. And let me show you some of the examples. Maybe I'm not going to be able to go over all of those examples today, but most likely even if there are a few examples that I do not cover today, I cannot cover today, I'll cover them inshallah next class, because I have selected some examples that will illustrate for you the power and the concept of the Fourier series. Okay. So let me share with you the entire screen. Let me know if you see my screen, just a minute.
We can see the screen.
Okay, thank you so much. Okay, look, I have listed in here something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, about 12, 13 different signals. Okay, I'm gonna go over most of them, but maybe not all of them. Okay, I just want to show you the power. What I did over the weekend, yesterday or the day before, is I went and created several signals that show you that you can always, any periodic signal, you can always represent it in terms of sines and cosines. Sines and cosines only. DC, the DC was the one. You remember the one, which was one of those signals. This is the DC, and all of the other signals are sines and cosines. By the way, the DC, you can always think of it as a cosine with frequency that is equal to 0. You know this. DC is a cosine with 2 pi multiplied by 0t. This gives you DC. So even if you want to think of all of those signals as sines and cosines, you can do that. So let me take the first one. So what I will do is I'll take each one of those signals, copy it, and move it to MATLAB. Okay. Let me run that code. Open. Okay. So let me run it. Okay. Continue. Okay. What I will do is I have created several signals. So let me plug in the first signal there, okay, and show you basically the shape of the signal. This is a triangular shape. I think it was, yeah, triangular shape. Although I was expecting, let me just check. Did it say triangular shape there? Okay. Yeah, triangle. Okay. Sorry, this was not the first one. Yeah, because I remember that the first one was not triangle. In fact, I have more than 13, maybe 15 or so. Well, so let me take the first one. This is the first shape. In fact, if you remember, I sketched this last time. I told you, do you think that the Fourier series can simulate this? Now, this is a periodic signal. If you notice, this is a periodic signal. Now, the period that I've selected for my periodic signals, I didn't select it to be equal to 1 second. I selected it to be equal to 2 seconds. In fact, it's the duration between the blue lines. You see those two blue lines, the vertical blue lines, this one and this one? This is the duration between, hold on, let me see. Okay. This is the duration between, or let's say this is the period of the of any periodic signal that I will do. I will always make sure that the periodic signal that I'm using have a period that is equal to 2. Now I can change it, but changing it is not going to add much. Okay. Now I am trying to represent those using so far nothing. I think, or I'm sorry, I'm using only the DC value. The DC value for this is equal to 0. Now, what do you see, by the way, in here? This is the signal. The red curve there is the signal that I'm trying to represent. The blue lines represent the duration, the interval that I'm trying to find the Fourier series over, or basically I'm trying to represent one period of that signal using the Fourier series. Okay, and here the bottom left, let's say, part in there, it shows you the different sines and cosines that I will add together to produce. Yeah, their addition will become equal to the signal that I'm trying to represent. Okay? And the green line in here, you see the green line there, is basically the addition of all of those. Yeah, again, what let me just clarify this. In here, you see the different components, the different sines and cosines. Each one of them is sketched separately. Okay, but when you add all of those together, they will become the green line in here. And in here, what you will see is the magnitude of the different sines and cosines. So, in fact, the first component in here, this basically shows you the frequency. This is zero frequency, or think of omega 0 equal 0. This is omega 0 equal to 1, omega 0 equal to 2, omega 0 equal to 3. I mean, this is the frequency of the different sinusoids and cosines, sines and cosines that I'm adding together. Okay? So and how am I showing it to you? I'm showing it to you using dots. Meaning in here, I need 0 DC. What this basically means is that, look, this point, the red dot there, indicates that I need 0 DC to represent this. Why do I need 0 DC? Because this signal does not have any DC value. The average of this is equal to 0. Look, half of it is above 0 and half of it is below. So its average point is going to be 0. So I do not need any DC to represent this. Now, if I click on this in here, it will show you, basically this slider in here will move to the right a little bit. Okay? So it will show you how much do I need of DC and how much do I need of cosine 2 pi omega 0 t and sine 2 pi omega 0 t. The red dots will represent the magnitudes of the cosine, and the blue dots will represent the magnitudes of the sine. Okay? Inshallah, with time you'll understand what I'm talking about. Huh? Let me just move. Look, if I add now 2 components, it happens that one of them is, look, the blue one is a sine. To be able to represent this, I need a sine. I don't need a cosine. Why? Look at this signal. This is an odd signal, the red one. Is it an odd signal or an even signal? This is, by the way, this is the 0. Is it an odd signal or even? It's an odd signal, isn't it?
Odd.
Yes, it's odd. Odd signals, you only need sines to represent them. Even signals, you only need cosines. Signals that are, why? Because the cosines are even, and we said that when you add even signals, you get even. Odd signals, if you add odd signals, you get odd. It's not like integers, gentlemen. If you add 2 odd numbers, you get even. But for odd signals, if you add 2 odd signals, you get odd. So if you have a signal that is odd, you only need odd signals, which are the sines, to represent it. A signal that is not even and not odd, you need basically both sines and cosines to represent it. This is why in here, if you notice, the blue, okay, represents don't worry about the BN. The blue basically represents the magnitude of the sines. The red represents the magnitude of the cosines. So I need a sine to represent this. Now, clearly, this green now is just a very raw, let's say, rough approximation of the red. Why? Because I want to represent a complicated signal like the red one using only a sine, DC and a sine. DC, I didn't need any of it. But if you look at the sine, okay, the sine is a smooth function, while the one that we have in red is kind of a complicated function. So you can, clearly, you're not going to get a good approximation. Let me add more. Okay. Now, the second component, if you notice, both the red and the blue, by the way, are on top of each other. In here, if you look, both the blue and the red are on top of each other. Maybe you don't see it, but I know that this is the fact. This is a fact, okay? Why? Because to represent this complicated function, I do not need cosine 2 pi multiplied by 2 omega 0 t. This component does not help me in representing this signal. That's why the representation of that signal turned out to be equal to, or let's say, the component at that frequency, I do not need neither the sine nor cosine to represent that signal. Okay? Right, let's see the next component. Okay. Now, if you notice, this is not a cosine, or I'm sorry, this is not a sine. It looks a little bit different. Let me go back. Look at the green curve in here. Look at the green curve. and see what's the difference between the green curve that you have now and this green curve. It's a little bit distorted. This one looks like a little bit distorted sine. It's kind of wider in here. I don't know if you noticed it, but it's a little bit wider. It's trying to approximate this, relatively speaking, complicated curve. So it added another component in here. Maybe you don't see it, but the blue here is slightly higher than 0. Just a little bit, because this is the amount that you need from this component to basically represent this. But clearly, again, this is not a good approximation. Let me go further. Let me add more. Now notice that as I added, some of the components were positive, some of them were negative. Yeah? But now if you notice, the approximation is getting better. If you notice now, the green is, I'm not going to say almost equal to the red, but it's significantly better compared to the previous ones to the red. Let me just take this and move it all the way to somewhere in here. Now it's going to take a while because my apologies. It's because of the way I programmed it. I'm sure that someone else who programs it maybe better will be able to do a better job in this. Okay? But let me show you. It will take maybe, I don't know, half a minute or so. As you see in here, I think you can see those dots appearing. Now the dots there are the different components, but the addition here is going to appear once it's done with all of those. And once it finishes, this reaches the end in here, which is going to be something like 115 different components in here. So I'm adding 1 plus a sine plus sine 2 omega 0 t plus sine 3 omega 0 t plus sine 4 omega 0 t and so on until sine 115 omega 0 t. So just give it 20 seconds or so. And trust me, maybe you can't see it in your screen well, but I can see some of those components above and some of the components are below. Now, you do not need, from the high frequencies, you do not need a lot. For example, the first component here required a lot of value of it, or its magnitude was, relatively speaking, large. Okay? But the other components there, I don't need as much as I needed from the first component. Notice in here, this is the low frequency. The higher frequencies were lower in amplitude, and as the frequency increases, their amplitude becomes smaller and smaller. Now notice how the green was able to approximately, let's say, it's again not perfect. I want to emphasize that, again, the green is not perfect. It's not exactly equal to the red. There are places in which it deviates from the red by, relatively speaking, large amount. But in other places, it's almost on top of the red. In fact, where does always, remember this, continuous curves, or let's say smooth curves, are easy to represent using sines and cosines. And I have some examples of those. Smooth curves, if you have a curve, like for example, cosine squared. Cosine squared is a smooth curve. You can easily represent it using sines and cosines. Or any curve that does not have any edges, any corners, any sharp edges, you can easily represent it using few sines and cosines. Next comes in difficulty signals that have some sharp edges, but no discontinuities. For example, like a triangular wave. You remember the signal that I put at the beginning? The triangular wave? A wave that looks like triangles. This is, let's say, second in difficulty in representation. But again, for example, if you needed to, let me say, okay, let me go to OneNote. And let me write it this way. For example, if I have a smooth, and then signal with corners. What I mean by corners are sharp changes. A line that is increasing and then suddenly it decreases, something like this. Corners. Okay, and then signals with discontinuities. Okay, and then signals with impulses. Okay, signals that are smooth, maybe you need something like, for example, signals that are smooth, you might need, for example, well, it depends on the complexity of the signal itself, but you might need, for example, 3 sinusoids. at different frequencies to represent it. Signals with corners, you might need 7 or 8 or 9 or 10 to represent it accurately. Signals with discontinuities, you might need, for example, 50 sinusoids. I mean, it depends on a lot of things, but I'm just giving you an indication. Now, signals with impulses, very often, you'll need maybe an infinite number of sines and cosines to represent it. And I'll show you this, in fact, as an example. Okay? So the more your signal becomes complicated, the more sinusoids you need to get a good approximation of it. Okay, Juan? Right. So let me go back to MATLAB and show you now a different signal. Yeah. Now, what I called by this, I called it limited inverted sine. Let me look at the other one, just to show you that this is not that different. First of all, let me take this all the way to 0, so that it does not, okay, it does not take a long time. Now, this is the second signal. This is not that different from the previous one, except that in the previous one, if you remember, those what they look like inverted sines or so, were going to 0 and then remaining 0 for a while and then going back down and so on. So this is like an inverted sine, except that the periods in here touch each other. Yani there's no region in which the signal is equal to 0. Okay? Let me just show you that I can also represent this. I'm not going to go to a very large value. But I'm going to show you that with maybe 30 or 40, I can represent it. Okay? Okay? Notice that the representation, again, is not perfect, but it's close. And always remember this. Look, in places where you have smooth region of the function, the Fourier series can approximate the signal with good accuracy. Where does the deviation happen? It always happens at the corners or at the discontinuities. The largest deviation happens at the discontinuities. Whenever you have a discontinuity like this vertical line in the function, you'll always see that the Fourier series has difficulty in approximating the signal at those locations. You see this thing in which it starts to go up and down, the Fourier series expansion. It goes up and down around the signal. This is called the Gibbs phenomena. Gibbs phenomena. Okay? And this is a very well-known phenomena that Fourier series always has. Whenever there is a discontinuity, the Gibbs phenomena will appear in the Fourier series because it has difficulty, let's say, in representing the signal. Okay? Right. Let me go to another signal, maybe more fun. Triangle wave. Now, the triangle does not have discontinuity. The triangular wave, at least that I'm showing you, does not have any discontinuity. Yeah. So you'll see that only few sinusoids or so, you can, in fact, represent it. In fact, I'm using too many here, too many sines and cosines. You'll get almost a perfect approximation. Look, do you see any deviation between the two? Unfortunately, I cannot zoom in here. Well, otherwise, I would have zoomed in to the peak in here or bottom there. Let's say those corners on top or on bottom. You see that there's this very small deviation from the two. Okay? Notice in here that to represent a triangular wave using sines, you need some DC. In this situation here, by the way, the DC is not equal to 0. The DC is 0.5. So I need some DC. I need the first component. The second component, I don't need anything. The third component, fourth component, I don't need. The fifth component, I need a little bit. And that's it. In fact, let me reduce this. Instead of being around 45, let me make it around 3. Look, only with 3 sinusoids, 3 components or so, I was able to get something that's very close. It's not perfect. And if you notice that there's some difference between the red and the green in here, at the peak in there and at the bottom in there. But maybe one more component or 2 more components would be more than enough. Okay? Now it's better. 2 more. It's even better and better. Okay? So just by having few components, you can represent the triangular wave almost perfectly. Okay? So I'll stop here, and I promise you, inshallah, next class, maybe we'll not go over all. Probably I'm not going to go over this one. I'll talk about the triangular wave, square wave, and so on. I'll talk about several of those. But the reason why I need to go over some of those is there are some concepts that you'll not understand unless you see the actual Fourier series expansion in real life. Okay? طيب يا اخوان, I promise you that I'll tell you about the material of the quiz. The material of the quiz, and I'll send it inshallah on WhatsApp again later. Okay? The material of the quiz will be the following topic. The convolution is not going to be with you, don't worry. The convolution, I'm saving it for your midterm exam. Okay? The material of the quiz will be the following. Last time, I think the quiz, we reached this. Okay? So it will be continuous time systems 7.7, or let's say item 7. And I think I have uploaded an updated lecture note. I think I have uploaded yesterday or the day before, which contains more discussion on this. In fact, I changed those examples and I solved them. Okay? And 8. And that's 8 and 9. Okay? So, yeah, basically it's before the because I think maybe the titles there or the topics have changed. It's basically it is this. Okay? Continuous time systems. Okay? And properties of continuous time systems, and how do you determine the properties of continuous time systems? And I have put an example in the lecture notes. I think I have uploaded it. If I haven't, I'll upload it right away. Okay? But I think I have uploaded it yesterday or the day before. Okay, Juan? So so this is going to be the material of the quiz. So the topic, which is continuous time, linear time invariant systems, is not with you. Okay? Yalla, have a good day. If you have any questions, I'll remain online. If you don't have any questions, inshallah, I'll see you tomorrow. طبعا the quiz we agreed that it's going to be Tuesday. Right? It's Tuesday. It's not tomorrow. Tuesday. تفضل محمد.
دكتور الماتيريال حق المترم لوين بيكون؟
Well, until now I haven't decided الحقيقة لأن I don't know where we will reach. But I'm guessing that it will include part or maybe all of Fourier series. And I expect that we'll spend something like 3 or 4 classes probably in the Fourier series. Okay? Probably. My guess is that whatever we cover this week is the material that will be included. Okay? يعني anything that we cover متى انتم الاكزام لكم؟
8 July.
8. Okay. Most likely I'm not going to include material from next week. Although the 8 July I think is on Thursday. Right? Most likely I think it's enough. If you have the material of 4 weeks, this is more or less something like half of the semester. Okay. In fact, let's even fix it. Okay. Whatever material we cover today is going to be included with you in the exam. Any material that we cover next week is not going to be included. Okay? But by this, this meaning this weekend, you'll have all of the material that you need to cover in the exam.
Thank you so much, Doctor.
Sure. Any other points or questions, gentlemen? By the way, your quiz, second quiz, well, I started working on it. صلحت يمكن إلى 12 or 13 of you, but I haven't. It's taking so much time. Well, so far, I have spent approximately 2 hours for 12 or 13 students. It's my fault. I put too many questions, let's say, in the quiz.
Take your time. It's fine.
No, I know that you want to see your result.
Yeah,
Whatever.
but it doesn't make much difference what time we get.
Thank you so much for your kind words. Thank you. Shukran. Any other questions, gentlemen? If you have questions or comments or complaints or